You know when you flip a switch and a light turns on instantly? Well, the story of what's actually happening inside that wire is one of the most fascinating and honestly misunderstood journeys in all of physics. So today, let's follow that spark and unpack the hidden world of electric current. So let's just dive right in with the big question. What is electric current? It sounds really technical and complicated, but the core idea behind it is actually surprisingly simple. It's not magic, it's just a flow. But, a flow of what exactly? That's what we're here to find out. All right, so here's our game plan. We're going to start with a really simple analogy, a river. Then we'll meet the actual particles that make up that flow. We'll figure out how to measure it, and then we'll peek inside the wire to see what it's really like in there. And stick around, because at the end, we'll run some numbers and uncover a paradox that is seriously going to change how you think about electricity. Okay, so to get our heads around this whole thing, let's use a simple analogy. Just picture an electric current like a river. Simple enough, right? But instead of water, this river is made of pure electric charge. And the more charge that flows past any given point each second, well, the stronger the current. And this brings us right to the official textbook definition. Electric current is simply the rate of flow of charge carriers. Think about it. For a river, the current isn't about how much water there is in total. It's about how much water flows past you every single second. It's the exact same idea here, just with charge. So, if the current is a river, what are the individual droplets of water? Well, in a typical wire, they're electrons. These are our charge carriers, the tiny, tiny heroes that are doing all the moving, making everything from your phone to your toaster actually work. Now, here's where it gets really, really interesting. The universe has this fundamental rule. The charge on these carriers is quantized. That's a fancy word, but all it means is that charge isn't some smooth, continuous fluid like water. Nope, it comes in tiny, indivisible packets. You can't have half a packet or a quarter of a packet. It is all or nothing. And this is it. This is the size of that fundamental packet, 1.6 times 10 to the power of minus 19 coulombs. A coulomb, by the way, is just the unit we use to measure an amount of charge. This incredibly small number is called the elementary charge. It's the smallest possible bit of charge that can exist all by itself. It's the charge of one single electron. Okay, so we've got our river of charge, made of these tiny packets. But how do we actually measure it? How can we count the total amount of charge that's flowed past a certain point in our wire? Luckily, there's a really simple way to figure this out. The total charge, which we call Q, is just the current, I, multiplied by the time it's been flowing, T. Think about it like filling a bucket from our river. The total amount of water you collect, that's Q, depends on how fast the river is flowing, that's I, and how long you leave the bucket there, that's T. So if you have a current of 1 ampere flowing for 1 second, you've officially moved 1 coulomb of charge. It's as simple as that. So that river analogy is great for getting started, but an open river is one thing. What's it really like for an electron inside a copper wire? Well, it's way less like an open river and a lot more like trying to move through an unbelievably crowded hallway. So if you're picturing that super crowded hallway, what factors are going to affect how many people can actually get from one end to the other per second? Well, the exact same logic applies to the electrons in our wire. What determines the total current? First up, we have N, which stands for number density. This is basically just how many charge carriers, our electrons, are packed into a given space inside the wire. Is our hallway totally jam-packed, shoulder to shoulder, or is there a little bit of room to move? This is actually what makes a good conductor, like copper, so great. It's just packed with free electrons ready to go. Next is A, the cross-sectional area. And this one is super easy. It's just how wide the wire is. A wider hallway means more people can squeeze through at the same time, right? Same thing here. A thicker wire means more electrons can flow. Then we've got the mean drift speed. Now this is a key one. It's not how fast the electrons are randomly bouncing around, which they do, crazily. It's their average forward speed. It's how quickly they're actually managing to shuffle their way down that crowded hallway. And finally, there's Q, the charge on each carrier. And hey, we've already met this guy. It's that fundamental quantized packet of charge that each and every electron carries. So, when you put all of those pieces together, we get this incredible master equation. The current, I, equals N times A times V times Q. It's so elegant. This one formula tells the whole story. The total current depends on how crowded the wire is, how wide it is, how fast the electrons are drifting, and how much charge each one is carrying. All right, let's put this powerful formula to the test. Our source material gives us some real experimental data that a student recorded. So let's play detective and use our equation to see if their numbers actually hold up to the laws of physics. So here's the data they collected. They measured the current, the drift speed, the number density, and the area of the wire. Looking at our formula, that gives us I, V, N, and A. The only thing missing is Q, the charge on each carrier. So let's rearrange the formula and use their data to calculate it. Okay, so we rearrange our I equals NAVQ formula to solve for Q. We plug in all the students' numbers, and this is the value we get. 1.1 times 10 to the negative 19 coulombs. According to their experiment, this is the charge per carrier. But wait a minute, does that number look a little familiar? Remember that elementary charge we talked about, the fundamental indivisible packet of charge? The true accepted value is 1.6 times 10 to the minus 19 coulombs. Our student's value, well, it's not just a little bit off, is it? And this is exactly the point the source material hammers home. Because charge is quantized, because it can only exist in those specific packets of 1.6 times 10 to the minus 19, the student's result of 1.1 is, well, it's physically impossible. You literally can't have a fraction of an elementary charge. So something in their measurements must be wrong. But here's the crazy thing. Even though the student's data was flawed, it actually reveals something completely mind-boggling about our electron's journey. It points us directly to a final, fantastic paradox at the very heart of electricity. Let's just look at that drift speed the student measured one more time. It's 1.3 times 10 to the minus 3 meters per second. That's just 1.3 times millimeters per second. I mean, that is incredibly, ridiculously slow. We are talking about the speed of a crawling snail. And this brings us to our final mind-bending question. If the individual electrons are just shuffling along at a snail's pace, how on earth can flipping a switch turn on a light all the way across the room instantly? The answer is that while the electrons themselves are slow, the electric field that's the signal that tells them to start moving travels through the wire at nearly the speed of light. It's like having a long tube packed full of marbles. You push one marble in on your end, and one pops out the other end almost instantly, even though no single marble traveled that whole distance. And that is the beautiful, totally counterintuitive truth at the heart of electric current.